Welcome to all of our 12th standard students. Today we are going to see about Kirchhoff's laws. It is used to find current and voltage in a very complex circuits. Which is called as a very complex circuits means circuits which contains two or more batteries and many resistors. There we cannot use the Ohm's law. Ohm's law is used only in a simple circuits. If it is a very complex circuits, there we cannot use the Ohm's law to find a current and voltage across any resistor in a electrical circuits. So that's why we are moving to see about the Kirchhoff's rules, or called as a Kirchhoff's laws. There we have a two laws we have. That is current rule and voltage rule. So we have two rules. In that, one is a current rule. Second one is the voltage rule. These two rules are used to find current and voltage in a very complex circuits. There we have a certain definition as well as the basic rules to use each rule. So that is going to see in that Kirchhoff's current rule, and it is also called as a first rule. Another name also we have for this Kirchhoff's current rule called as a junction rule. Why we are called this first rule or current rule as a junction rule means we are applying the Kirchhoff's first rule for a junction in any closed circuit. Junction in a closed circuits. That's why that Kirchhoff's current rule is a first rule and also named as a junction rule. There we have a statement. What statement we have means in a complex circuits, any one of that junction we are going to take, and in that junction some of the currents are moved towards the junction and some of the currents may be move away from the junction. But what amount of total current moved towards the junction is equal to amount of current away from the junction. That's why we have simple statement for that Kirchhoff's first rule. Statement we have here, we are taken algebraic sum. Why we are taken algebraic sum means there we have some basic rules. So towards currents are taken in positive, away currents are taken in negative. That's why in the statement algebraic sum of currents in any junction in a circuit is equal to 0. This is the very good statement. We are saying algebraic sum of currents means many currents, two or three currents move towards the junction, or one or two current maybe move away from the junction. That's why algebraic sum of currents in any junction in a circuit is equal to 0. There we have some basic rules. That basic rules, what are the basic rules means, one is current towards the junction is taken in positive. And next one is, next rule we have current away from the junction is taken in negative. These two basic rules we want to follow very carefully. And there we have one example diagram in a total circuit. One of the junction we are going to take on. Junction A is going to take on. Example, there we have a junction A. Some of the currents may be move towards the junction, some may be move away. We are going to represent the arrowhead, whether it is move towards or move away. Here, arrowhead is towards the junction. This arrowhead also move towards the junction, but here away. These three are away, and each and every one current representation is I1, I2, I3, I4, I5. In our diagram, I1 and I2 are move towards the junction, I3, I4 and I5 are move away from the junction. So that's why this value is taken in positive. I1 as well as the I2 is taken in positive, but these three is in negative value, very simply. But we want to take a total algebraic sum. Then only follow our rules. That's why, according our diagram, plus I1 plus I2 plus is a minus I3 plus minus I4 plus minus I5 equal to 0. But these three, I3, I4, I5 are in negative value. That's why I am going to take on these three in other side and take on I1 plus I2 equal to I3 plus I4 plus I5. So these two currents, some of the currents are moved towards the junction. This alone, this total current alone, move away from the junction. And another one we have basic current definition we have. In that basic current definition, formula we have I is equal to Q by T. We can define the current as a rate of flow of charge. Rate of flow of charge. That is, what meaning we have means, current flows towards or away the junction means charges are moving towards or away. That I1 and I2 passes how much amount of charges towards the junction, that total charges only move away from the junction. At a junction, charges neither created nor destroyed. That's why the first rule is obeys the conservation of that electric charge. Obeys the conservation of the electric charge, and it conserves the charges we can see. This is the rules, very simple rule to follow in our very complex circuits. First rule it is. Now we are going to see that example problem for Kirchhoff's first rule. That Kirchhoff's first rule is a junction rule. Number of resistors connected at that junctions. In that some of the resistors, current is moving towards the junction. That we are going to take on. First one is a current I1. Its value in our problem given 0.2 ampere. Next one, direction is this. There current I2, their value is 0.4 ampere. Next one, towards the junction, that can be taken I3. I3 is equal to 0.6 ampere. Then here, next resistor, there we have a current 4, I4. Their value is 0.5 ampere. Another resistor, we have a current I5 towards the junction. That's value is 0.7 ampere. And another one is there, away from the junction, that current is unknown current. For that unknown current, I am representing I alone. The known currents, sign convention we want to take. So first current towards the junction, that's why it is a positive value. Second current away from the junction, that should be taken in negative. Third current towards the junction, that is a positive. Fourth current away from the junction, that can be taken in a negative. Fifth current towards the junction, that is a positive. But that unknown current away from the junction, that is taken in negative. So we are going to apply first rule. The first rule is nothing but algebraic sum of current at a junction in a circuit is equal to 0. So algebraic sum we are going to do. That is I1 value we have, that is a positive value, 0.2 ampere positive. Next I2 value, that is a negative, 0.4 ampere negative value because away from the junction. Then I3 we have, that current is towards the junction, that is taken in a positive value, plus is 0.6 ampere. Then fourth current away from the junction, that's why minus 0.5 ampere. And fifth current is towards the junction, that is plus 0.7 ampere. Another current is unknown current. That direction is represented, but away from the junction, that's why minus I equal to 0. In our equation, we are going to take on that minus values are one side and the plus values another side. The plus values 0.2 ampere plus 0.6 ampere plus 0.7 ampere one side. Then negative values are taken in the right side, that is 0.4 ampere. Then another one is plus 0.5 ampere plus I. This total value is 0.9 ampere. These total values 0.2 plus 0.6, 0.8 becomes, then 0.8 is going to add with 0.7, there we have 1.5 ampere equal to 0.9 ampere plus I. Then I value we want to find, I is equal to 1.5 ampere minus 0.9 ampere. Then its value is 0.6 ampere away from the junction. Away from the junction. It is a example sum for Kirchhoff's first rule. Next we are going to see that Kirchhoff's second rule. Second rule, we have some alternate names. That is voltage rule or loop rule. Why we are saying it is a loop rule means this second rule is going to apply for one of the closed loop in our given circuit. So we will see that heading. Kirchhoff's second rule. There we have a statement for that second rule. What statement we have in our second rule means algebraic sum of product of current and resistance in each part of any closed circuit is equal to total EMFs in that closed circuit. That is, statement we have algebraic sum of products of current and resistance in a closed loop, or we call it as a circuit, is equal to total EMFs in that closed circuit. So, definition is algebraic sum of product of current and voltage, where the current and resistance in a closed circuit is equal to total EMFs in that closed circuit. This is the statement. There we have some basic rules also. That basic rules we are going to see. One is resistor with current, or resistor, one end is represents A, another end is represents B, and the current is moving in this direction. So, if we move A to B, there we are moving in the actual current flow direction. Then that value, product value is I into R, product value is a voltage. That voltage value is taken in a positive I into R. If we move from A to B, actual current direction we are moving. That's why the product value is a positive. Suppose if we move from B to A, our movement is opposite to the direction of that actual current flow. At the time their product value is taken, V is equal to minus IR. Very careful that the product of current and resistance value, when we are going to take on positive, when we are going to take on negative, means we moving our circuit in the same direction of the actual current flow, they are positive. If we move opposite direction, that is a negative. Another basic rule we have, rule 2. For a cell we have a negative polarity and a positive polarity. EMF of the cell can be taken as a E. Ends may be represented as A and B. Actually, current externally supplied by that cell is in this direction. Now we move from A to B. From A to B means first negative polarity, next one positive polarity. If you move like that, what direction that the cell is supplying a current, same direction we are moving. So going from A to B, then EMF is a positive. Otherwise, suppose we may move from B to A. Going from B to A, then EMF is negative EMF want to take on. These two rules we want to follow for applying a Kirchhoff's second rule. There also we have a example diagram. That is, the example diagram is there. One of the cell we are going to take on. that a cell is going to connect with a number of resistors. Five resistors we are going to tackle. Each one we are going to name that R1, R2, R3, R4, R5. Their currents I1, I2, I3, I4, I5. And here we are representing a capital E for that cell EMF. This point junction may be represented as A. This point may be represented as a B. This may be taken as a C. So for this diagram, we are going to apply Kirchhoff's second rule. Loop rule it is. That's why we are going to apply for the loop. Taken loop. Loop. Movement direction is very carefully you want to tackle. The movement direction, first I start from E, A, and here C, then end of that E. That is E, A, C, E. Which rule we are going to apply? Kirchhoff's voltage rule. We named as a KVR. Kirchhoff shortly named as a KVR. There also want to use that rules properly. They are first moves from E to A. E to A. Between that R1 resistor we have, through that I1 current flow. We are moving same direction as the current flow direction. That's why their product value is taken in the positive. I1 into R1. Then A to C we are moving. A to C. Between that one resistor R2, their current flow is I2. We are moving same direction as the actual current flow. So their product value also positive. Then C to E. Between C and E, we have a R3 resistor. Our moving from C to E, same direction as the current flow direction. That's why we can take an I3 into R3 equal to, then what the EMF we have, that we are going to represent in the right side of our equation. So one EMF is there, E EMF, move in what direction we are moving, the same direction that cell is supplying a current, that's why that is taken in a positive. Okay. One of the loop we are taken in our circuit and represent express the equation. Next equation also we can represent the taken loop. Taken loop, that is we are starting from A, B, C, and once again come to that A, B, C, A. So what are the resistors, what are the current flow we have, that we want to observe our diagram. There first we start from A to B. There are R4 resistor and we have I4 current flow. In what direction we are moving? The same direction the current is flows. That's why their product value I4 into R4 positive value plus further movement from B to C. There we have R5 resistor, actual current flow direction and our movement directions are same. That's why that is a positive. I5 into R5. Then our movement is C to A. C to A. There are two resistors we have, but our movement direction is opposite to that actual current flow direction. That's why their product value is negative, minus I2 into R2 equal to no EMF cell in our taken loop. That is what loop is that? A, B, C, A. That's why zero EMF in that loop. Now we are going to see these two equations. In the first equation, the product of second current and resistance value is taken in a positive. But in the second equation, the product of second current and the second resistance is in a negative, because in the first time we move current direction as our movement directions are same. But second time for that closed loop A, B, C, A, the movement for that current direction in that I2 is opposite the direction of that actual current direction. That's why we are taken in a negative. And the same thing, what energy this cell can be supplied for the flow of current, that energy only consumed by these resistors. That's why energy delivered by the cell equal to energy gained by all the resistors, energy absorbed by all the resistors. That's why it obeys that conservation of that energy, law of conservation. It obeys law of conservation of energy. And the same thing, at the time of applying this Kirchhoff's second rule, the current flows must be a steady current flow, not a varying current. If it is a steady current means, then only we can define certain value. If it is a varying current, we cannot define. So that's why we are carefully handle this equation at the time of steady current flow in our network. If it is a varying current flow, there we cannot apply that Kirchhoff's second rule. So that's why the Kirchhoff's first rule and the second rule are very simple. First rule is junction rule, second rule is loop rule. That first rule is nothing but algebraic sum of current at a junction is equal to 0. Second rule is very simple, algebraic sum of products of current and resistance in each part of a closed circuit is equal to total EMFs in that closed circuit. These two laws are very useful for your complex circuit applications. If it is a simple circuits, we can apply the Ohm's law only, that is enough. If it is a more complex circuits, there we cannot apply that Ohm's law, there we must use that Kirchhoff's laws, first rule and second rule. First rule is for that applying junction, second rule is for applying a loop. Okay, very well, we go through that book and go through your example problems and clear that idea. Okay, thank you.